In this video, we are going to have Cayley's theorem, generalized Cayley's theorem, and index theorem for non-simplicity. So first we'll have Cayley's theorem, which states that every group is isomorphic to a subgroup of A of S for some appropriate S. Now, given any set S, we know that A of S stands for the collection of all bijective mappings from S to itself. All those bijective mappings from S to itself. What is S? S can be a set, and all the bijective functions from S to itself are members of our A of S. So to prove the theorem, actually we have two claims in that. First we shall assume that G to be the given group and S to be G. We consider a G in capital G, and we define this mapping tau G from G to itself by x tau G equal to xg. That is, tau G takes any element x to xg for every x in G. We are writing the element to the left of the mapping, and here we have xg. Now, having defined this rule, we'll prove that this is well defined and one-to-one onto, so that it can be present in A of S. So tau G is well defined for the reason that when we take x to be equal to y, two elements in the domain equal should imply the images to be equal for well definedness. So we consider x to be equal to y, then xg, that is, we post multiply both sides by g, so you get this, and this by this definition is nothing but the image of x under tau G. This is image of y under tau G. So this shows that elements in the domain equal implies elements in the codomain to be equal. So you have, that is, the images, corresponding images in the codomain to be equal implies that tau G is well defined. Now for one-to-one, we'll have to just retrace the steps. We consider the images to be equal in the codomain, and we have to prove that the pre-images are equal. So this one gives, that is, x tau G equals y tau G implies that xg equals yg, and that in turn implies x equal to y by right cancellation law. So that in turn tells tau G is 1-to-1. Now we'll consider for onto an element y in G. Here both domain and codomain being the same, we mention that this G refers to codomain. Let y belong to G, then there exists yg inverse in the domain such that, see, we have considered y in G. Already G in G exists. G is a group. So yg inverse is present in G, and that is in the domain such that yg inverse, the image of this under tau G, gives us yg inverse G, and that we have y itself. So we started with y, and we have said that for that the pre-image is yg inverse in the domain, and when tau G takes it the codomain, it comes as y. We started with y, and when we applied this tau G, we are getting back that y. So this is the pre-image. Yg inverse is the pre-image of any y in G in the codomain. So this tau G is onto. So for every G in G, we have proved that tau G is a member of A of S. A of S is the collection of all bijective mappings from S to itself. Here S is taken as G. So we have this tau G to be a member of A of S. Now in the second claim, this is the main part, that G is isomorphic to a subgroup of A of S. So for that we define a mapping, say psi from G to A of S by psi of G is tau G for every G in G. So this is how psi is defined from G to A of S. You have G and you have A of S here. That is the codomain. You are defining a mapping psi from G to A of S. So it takes any element G to tau G. We want to show that the psi is and this rule is well defined. So again, two elements in the domain should be taken as equal, and we have to show that the corresponding images are equal. G equals G prime should imply psi of G equals psi of G prime. So this, when we pre-multiply both sides by x, gives us this. This is nothing but x tau G. By the definition of tau G, we have this. And this is true for every x in G. So as the images are equal, the mappings must be equal. But tau G is nothing but psi of G, and tau G prime is nothing but psi of G prime. So psi is well defined. Next is psi is a homomorphism. Now since to prove this, what we first establish is tau G composition tau H is tau G H. This we first establish. To establish this, these two being mappings, we'll have to show that the corresponding images are equal. So we consider x. What is x? X is any member in G. So we have x, the image of x under tau G composition tau H. By the definition of composition of mappings, you have this x tau G of tau H, and this is xg tau H, and this again, when we apply tau H, gives us this, and by associativity we have this, and this is nothing but the image of x under tau Gh. So this being true for every x in G, the images are equal, therefore the mappings must be equal, and that in turn gives that tau Gh, this is nothing but psi of Gh, and this is nothing but psi of G composition psi of H. This becomes, so psi of Gh, which is tau Gh, and tau Gh is tau G composition tau H, and this is nothing but psi of G composition psi of H. Therefore psi is a homomorphism. Next we prove that psi is 1 to 1. For that we consider the kernel of psi, because psi is a homomorphism, we can talk about kernel. So it is all those elements in the domain. It is all those elements in the domain which are mapped onto identity element of the codomain, that is identity mapping. Now this is set of all G in G such that psi of G is tau G, that is identity mapping on S. Now this is set of all G in G such that x tau G, because the mappings are equal, the images must be equal for every x in the domain of tau G. So you have for every x in G, we have this to be true. So it is the kernel psi is nothing but the set of all elements in G for which xg equals x for every x in G. So it is only, that is G in G commutes with, it gives back G in G. What is that G in G? Which gives back whatever element is multiplied with that. So it can only be the identity element. So we have kernel psi to be just singleton E. So that because kernel psi is singleton E, we conclude that psi is 1 to 1. So this is one way of proving that psi is 1 to 1. Alternate method is we consider the images to be equal and show that the pre-images are equal. So psi of G equals psi of G prime implies tau G equals tau G prime. As mappings are equal, the images must be equal. So you have this, and by the definition of tau G, you have this step, and by left cancellation law, you have this. So this implies psi is 1 to 1. Now this part, in the same way only, we are going to have in the generalized form of Cayley's theorem. That is why this is discussed. So either to prove this part in the case of Cayley's theorem, either this or this method can be used. Now since psi from G to A of S is an onto homomorphism, we can always find a subgroup of A of S such that G will be isomorphic to that subgroup of A of S. An obvious one will be psi of G, because psi is a homomorphism, G is a group, means psi of G will be a subgroup of A of S. So that subgroup, we can have it as psi of G also. So we have here we can find a subgroup Okay, we can find a subgroup so that this G will be isomorphic to, it will be isomorphic to that particular subgroup. So the obvious one will be psi of G. So that proves the Cayley's theorem. Now in the generalized form, what we are going to have is, if G is a group and H is a subgroup of G, and S is the set of all right cosets of H in G, then there is a homomorphism theta of G into A of S, and the kernel theta is the largest normal subgroup of G which is contained in H. So we have G to be a group, H to be a subgroup, and S denotes the set of all right cosets of H in G. All those elements which are of this form, either HG or HX, the thing is X should range over capital G. So this is the collection S that we have in this statement, and of course A of S is collection of all bijective mappings from S to itself. So as before, we will define tau G from G to G. So how it is defined in this case now? Let G be the given group and H a subgroup of G, and let S be the set of all right cosets of H in G. Let S be G, as we did in the previous case. Now if G belongs to G, we define tau G by tau G from G to G by X, because any element here being a right coset, we have Hx, the image of Hx, and tau G to be Hxg. Hxg is the image of this and a tau G. Now we'll prove that this tau G is well defined. Tau G is 1 to 1, tau G is 1 to. Now once we have this, only then we can have our tau G to belong to A of S. So just to have tau G to be in A of S, we need to have this tau G to be 1 to 1 on to 1 1 and on to. So we have remember, even though G is taken as S, here S does not have any structure. In this case, S is considered as only a set of right cosets. Even though we write G to be S for appropriate S that we mentioned there, So like that, here S is taken as G, doesn't mean that S is a group, even though G is a group. It can be a group only when H is normal, not otherwise. So here there is no meaning in saying that tau G is a homomorphism. So that is not established here. Tau G is just 1 to 1 and on to. Now let for well-definedness, we have to consider two elements in the domain to be the same, and we have to have the corresponding images to be the same. So let Hx be equal to Hy, then this set will be equal to this set, and this is nothing but Hx tau G, the image of Hx under tau G, and this one image of Hy under tau G. So this shows that tau G is well defined. Now for 1 to 1, we'll assume the images to be equal and prove that the pre-images are equal. So once we have this, then by the definition of tau G, you have this step, and this in turn implies, see, we know that HA equals HB if and only if AB inverse belongs to H. HA equals HB if and only if, this is a result already established in one of the videos. So you have this result here that we use to prove the pre-images are equal. So you have this to be Xg. So this is A say and this is B say. So that you will have AB inverse A Xg B Yg. So B inverse. So this is what you have. And this A dot B, the whole inverse is B inverse A inverse. So this will be G inverse Y inverse. And already you have Xg here. So this in turn gives us XY inverse belonging to H. But again, make use of the same result to conclude that this is Hx equal to Hy. So tau G is 1 to 1. Images equal should imply pre-images equal for tau G to be 1 to 1. Now for on to we shall consider hy in the codomain G. Then we can have hyg inverse in G such that like in the previous case we have this hyg inverse, the image of that and tau G is hy itself. So now we come to the main part. So for every G in G we have produced tau G in AFS. Now what we need to prove in the main proof is there is a homomorphism theta of G into A of S, and once you have homomorphism, we can talk about the kernel, and this kernel is the largest normal subgroup of G which is contained in H. So for that we define theta from G to A of S by theta of G is tau G for every G in G. First we prove that this is well defined. So we'll have to consider two elements in the domain to be the same, and from this we can easily have hxg to be equal to hxg prime for every hx in S or rather G. So that in turn gives hx tau G equals hx tau G prime. This is true. We said already that this is true for every hx in G. For every hx in G, so you have the images hx tau G to be equal to hx tau G prime, but the images are equal means the mappings must be equal. So tau G equals tau G prime. This is true for every hx in G. So images equal should imply the mappings must be equal. So you have this, and this is nothing but theta of G and this is theta of G prime. So theta is well defined. Next we prove theta to be a homomorphism. So for that, as we did in the previous case, we will establish this tau G composition tau H as tau GH. To establish that, we will prove that the images are equal. So for that only we have considered this. For every hx in G, we can consider this hx tau G composition tau H. So by the definition of composition of mapping, it is hx tau G, and that is nothing but hxg. The image of that under tau H gives us this, and this in turn gives this, which is nothing but the image of hx under tau GH. So as the images are equal, the mappings must be equal. So you have this, and this is nothing but theta of GH, or rather we can now consider theta of GH, and by the definition of theta, it is nothing but tau GH. From here we have tau G, this to be tau G composition tau H, and this is theta of G and this is theta of H. So your theta is a homomorphism. So that proves the first part of this claim 2. So this proves first part of the second claim. Now let K be the kernel theta. We shall denote kernel theta by capital K. It is all those x in G for which theta of x is identity mapping. And theta of x is defined as tau x. So we have this. So it is all those x in G for which hg tau x is hg for every hg in G. And this is nothing but theta of all x in G. The way in which tau x is defined, we get this for every hg in G. But again, we make use of this result, HA equals HB if and only if AB inverse belongs to H. So that is used here so that you have GX G inverse belonging to H. And here where do we have our G? HG belongs to G. G is collection of right cosets that we have. So naturally our G should be there in capital G. So you have this. So kernel theta is nothing but this. We shall name this as 1. Now in the second part we have to show that kernel theta is the largest normal subgroup. So to prove that we have to have our K to be first contained in H. So actually this should have come earlier. I mean after defining this we have this one, that is kernel theta is contained in H, and to have that n to be, K to be the largest normal subgroup, then we have this part. So this has to come first and then only this discussion. So it has to come here. So what does it say? Kernel x belongs to kernel theta should imply x belonging to h. So if x belongs to kernel theta, then theta of x equals I, which is the identity mapping in A of S. And theta of x is tau x, so that is equal to I means we have this. So you have the image. Actually, this should have been written here, tau x. The representation, see, when you write the elements to the left of the mapping, then we'll have to have that throughout. So hx tau g should be equal to, hg tau x should be equal to hg for every hg in yes. Now in particular, we have this one to be HE, so you have, it is true for every HE, so HE is also present, so you have in S, so we have this to be true. And this in turn gives HEX to be equal to HE, and that in turn gives HX equal to H. So we have our X belonging to H, X belonging to kernel theta implies X in H, so kernel theta is contained in H. Now if n is a normal subgroup of G which is contained in H, n must be contained in K. If we prove that, then K will become the largest normal largest normal subgroup contained in H, and it happens in G. Now let n belong to capital N. This implies that G and G inverse belongs to n because n is normal in G. This is true for every G in G. Now this implies that G and G inverse belongs to H because n is contained in H. That is given. So if G and G inverse belongs to H means here from this first equation, from here we have our G and G inverse belongs to H means this one should be there in kernel, that is K. So n belongs to K. So we have n to be contained in K. Thus kernel theta is the largest normal subgroup of G which is contained in H. K is contained in H. K is contained in H, and n is also contained in K. N is any other normal subgroup which is contained in H, that's our assumption, and that is contained in K, which means that K is the largest normal subgroup of G which is contained in H, and the whole lot is happening in G. Now the index theorem for simplicity. Simplicity means when do we say that G to be simple? A group G is simple if its only normal subgroups are singleton E and G itself. So in between these two there should not be any other, that is there should not be any proper normal subgroup for G. Only then we can say that G to be simple. So we have to prove that if we are given certain conditions. What are they? If G is a finite group and H is different from G as a subgroup, that is H is a proper subgroup of G, such that order of G does not divide IH factorial. Now I of H, it is nothing but the index of H in G. Index of H in G is the number of distinct right cosets of H in G. So if order of G does not divide IH factorial, then H must contain a non-trivial normal subgroup of G. So H must contain a non-trivial normal subgroup of G. In particular, G cannot be simple. So if it has a non-trivial normal subgroup, because we have that trivial subgroups to be only these two. So other than this, your G should not have for it to be simple. But what we are going to say here is G cannot be simple, which means other than these two, this G has a normal subgroup. That is what we are trying to prove. G cannot be simple means other than these two, we have at least one proper normal subgroup. So first we will consider G to be a finite group and H to be different from G. That is, H is a proper subgroup of G. And what is given, order of G does not divide IH factorial, is named as statement P. Now we claim that H must contain a non-trivial normal subgroup of G. That is, H must contain a normal subgroup other than singleton E and G. Now to prove the claim, we make use of the above theorem. So from the above theorem, we have that kernel theta to be the largest normal subgroup. Kernel theta is the largest normal subgroup of G, which is contained in H. Now if we can show that this kernel theta can neither be G nor singleton E, then that will serve the purpose. So kernel theta is contained in H from the previous one, and that is different from G, so kernel theta cannot be G. Okay, so proof of the claim is by the above theorem we find that kernel theta is normal subgroup. In fact, it is the largest normal subgroup of G. So to prove the claim, it is enough to prove that kernel theta is different from G and different from singleton E. Why it is different from G is because kernel theta is contained in H and H is not equal to G given. So you have this. So that proves the first one. And suppose we have kernel theta to be singleton E, then theta becomes 1 to 1. So your theta from G to A of S is 1 to 1 homomorphism. So this in turn implies that G is isomorphic to the subgroup theta of G. So we can, and this is by the previous theorem, Cayley's theorem, that when we have 1 to 1 homomorphism, then G will be isomorphic to a subgroup of A of G, A of S. G is isomorphic to. So this in turn implies by Cayley's theorem, this is what we have. This theta of G we shall name as say some M. So we have order of G to be order of theta of G. Why? Because this G will be isomorphic to, that G will be isomorphic to that theta of G, as we have already theta to be 1 to 1 homomorphism. Now that theta of G is the image set, so naturally you have G to be isomorphic to theta of G. So in that case, order of G is finite, so order of G must be equal to order of theta of G, that is order of M. Now by Lagrange's theorem, M being a subgroup of A of S, order of the subgroup should divide order of A of S. And so this in turn implies that order of M being order of G divides order of A of S. But what is order of A of S? It is nothing but IH factorial. Why it is IH factorial? Why is order of A of S is IH factorial? See, we know that whenever S has n elements, that is S is the set consisting of say n elements. S is the set of n elements, say 1, 2, 3 up to n, then the Sn, the collection of all permutations on these n symbols, should have n factorial elements. It should have n factorial elements. This result is known to us already. So here S is nothing but the collection of all right cosets, and the number of distinct right cosets is nothing but the index. So S has I of H elements. So order of S being n, we have order of Sn consisting of n factorial. Here order of S is IH. So order of A of S, this Sn, because S has n elements, we denote that. Otherwise this is order of A of S. This means order of A of S. A of S is denoted as Sn when we have S consisting of n elements. General notation for this is A of S. So if S has n elements, order of A of S has n factorial elements. And here order of S is I of H, the index of H in G, that is the number of right cosets of H in G. And if this is I of H, then order of A of S must be IH factorial. But that contradicts statement P. Statement P is order of G does not divide IH factorial. So this contradiction tells us that kernel theta cannot be singleton E. So thus kernel theta is the required non-trivial normal subgroup. So as kernel theta is a normal subgroup of G which is neither singleton E nor G, by the definition of a group which is simple, we conclude that G cannot be simple. A group G is simple if its only normal subgroups are singleton E and G. Kernel theta is normal in G, but it is neither singleton E nor G, and therefore kernel theta acts as a proper normal subgroup. If any G has proper normal subgroup, it cannot be simple. So you conclude that G cannot be simple. So this proves this index theorem for simplicity of a group G. Thank you.